Welcome, everyone. Thanks for joining me for this explainer. Today, we're going to take a fascinating journey into the unseen, microscopic world beneath our feet. We are zeroing in on the mechanics of soil moisture, specifically how soil actually holds on to water and how we map those invisible forces. Now, as a heads up, everything we're covering today is drawn exclusively from our provided source materials, no outside assumptions, just straight facts on a process that is absolutely fundamental to plant growth and environmental water movement. And trust me, the actual mechanics of it are incredibly surprising. To get us grounded right from the start, consider this idea directly from our source material. Soil serves as a regulated reservoir for water. Think about that for a second. We so often just think of soil as, well, dirt, right? But as it takes in precipitation and irrigation, it's actually acting as a highly active, regulated management system. It's a living reservoir. Here's our roadmap for today. First, we'll look at the soil-water reservoir. Second, the microscopic forces of retention. Third, decoding characteristic curves. Fourth, comparing soil types. And finally, why soil water matters.
Let's dive right into Section 1, the soil-water reservoir.
So, what exactly is soil water? The source defines it as the liquid phase of the soil that fills part of the pore spaces established between the solid particles. And the text notes that this liquid phase is just as critical as the solid and gas phases of the soil system. Why? Because water is the ultimate solvent for most plant nutrients. It's a primary requisite for plant growth and literally influences the life of the plant at every single stage. Moving right along to Section 2, microscopic forces of retention. We know plants get their water from the soil, but how does the soil actually keep it there? Well, water is first absorbed with a D, meaning held onto by soil colloids like clay. Silt and sand actually do very little of this specific work. You can think of the electrostatic forces on these tiny colloidal particles almost like magnets. Because water molecules are dipolar, they attach to the particle with their positively charged end, leaving their negative end facing out. Then, in a successive chain, another layer of water attaches to that negative end, and it just keeps stacking. Eventually, as that water layer gets thicker and thicker, the magnetic orientation gets weaker. At a certain distance, the water molecules stop orienting like magnets, and regular liquid water, or capillary water, appears. If there's still more moisture available after that capacity is hit, gravity simply pulls it downward and it drains off. Now get this. This is a completely counterintuitive fact from the text. When we look at those inner layers of water, the ones held directly against the surface of the clay particle, it's believed they are actually quite different from ordinary liquid water. In fact, it's non-liquid. It is far more dense and viscous compared to the water you drink from a glass. It is only in those outer layers, where that magnetic orientation finally ceases, that ordinary liquid or capillary water actually begins. Mind-blowing, right? All right, Section 3, decoding moisture characteristic curves. So how do we measure this? We use a soil moisture characteristic curve. This maps the water retained by the soil against different matrix suction values. Matrix suction is basically just a measurement of how hard the soil is pulling on the water. And the term retention here is used as a catch-all to cover both the uptake of water and its release. For example, the desorption curve, which tracks how water is released, starts at full saturation and shows how much water is retained as that suction gets progressively stronger. Notice that these curves are highly nonlinear. They have a very distinct swooping shape. The source text points out that because of this, for a given change in water content, the change in matrix potential will be different at different points on the graph. To decode the math into plain English, there is a gradual decrease in tension with increased soil water content, and vice versa. Basically, as the soil gets wetter, the tension holding that water gradually drops off. Let's move to Section 4, comparing different soil types. When we compare soil textures like clay, loam, and sand, the curve for clayey soil sits much higher on the graph. That shows us it holds significantly more water at a given tension than the loam or sandy soils do. We see a similar dynamic when looking at soil structure. A well-granulated, aggregated soil has a lot of total pore space, but a compacted soil curve demonstrates that compact soils hold water with much greater suction than loose, aggregated ones. And this brings us to a really profound paradox in soil mechanics. Yes, clay holds way more water at a given tension than loam or sand, but it does so tenaciously. In fact, much of the water in clay soils is held so incredibly tightly that it becomes completely unreachable by plants. The soil might have a massive reservoir of moisture, but the suction forces are so incredibly strong, the plant roots simply cannot win the tug of war. To put a fine point on this, let's look at the actual numbers from the source. If you apply the exact same pulling force, specifically 15 bars of metric tension, to two different soils, the results are drastically different. A sandy loam will contain 5% moisture at 15 bars of tension, but a silty clay loam, it will contain 12% moisture. The clay loam is holding more than double the moisture under the exact same amount of tension force. Finally, let's wrap up with Section 5, Why Soil Water Matters. These retention curves aren't just academic exercises. They are absolutely vital for understanding how water moves in soil and how plants survive. The importance of soil water scales all the way up to profound ecosystem impacts. As we mentioned, it dissolves and carries nutrients to the plants, but it also drives the very process of soil formation itself. It makes the soil biologically active, supporting all kinds of flora and fauna. It literally carries dissolved oxygen down into the soil. And on a macro level, it acts as a thermal regulator, keeping the soil from getting too brutally cold or too scorching hot. It is truly incredible to realize that the vibrant macro-level ecosystems we see all around us are entirely dependent on dipolar water molecules stacking onto negatively charged clay colloids in states that aren't even fully liquid. So I'll leave you with this thought. From a dense, microscopic layer of moisture to a massive, thriving ecosystem, how well is your soil's reservoir functioning? Thank you for exploring the unseen mechanics of soil water with me today, and I hope this explainer gave you a totally new perspective on the ground beneath your feet.